Hi, welcome everybody. Thanks for joining my talk. So in our team, we've been working on GenAI for quite a few years now, and specifically looking at how it may transform and augment how software gets developed and how software applications and systems are being built. In this talk, I'll present our vision and iterate, okay, how we may in the future partly need to rethink or adapt how future software systems should be designed from the ground up to take into account this new technologies, new capability of GenAI, which imposes some additional complexities compared to traditional software systems. Today, I'll focus mostly on the why we believe this is necessary, and I'll present some additional ideas and perspectives and thoughts. If you want to read more, there's a paper. I also have a poster, I think this evening, where we can, if you're interested, talk into more detail. So, as we're all familiar, last few years, and actually the revolution started already many years before ChatGPT, but since ChatGPT became quite popular and to the masses, we've seen a lot of improvements and a lot of change and radical change in what this technology could mean for people, but also for building software. Last year or 2 years ago, we saw the rise of agents on top of large language models, which basically gives LLMs the indirect access to interact with other systems. And then since this year also there's an evolution to also not just let them blurb stuff, but actually think and reason how to solve and tackle a particular problem, and there's a lot of work ongoing there. But not only with respect to traditional kind of large language models and text-based handling, there's also a lot of evolution towards other media modalities. Think of image generation, music, audio, and even now video generation gets quite spectacular results. Although in our team, we're focusing mostly on the more traditional large language models and agentic approaches. Another evolution that we're seeing more recently is the shift from using this technology, GenAI, in you could say more passive chatbot type of applications that you give a request as a user, it does some computation and you get the result, to more proactive way of working, where agents driven through GenAI, driven through LLMs, are actually more autonomously, collaboratively, asynchronously doing tasks based on some high-level specification, even though there may not be an explicit command to do X, to do Y, in a very synchronous fashion. And so the obvious question then is, okay, what does it mean for having future software systems that may have one or more of these GenAI components embedded into them? And if you think about the traditional software system, it's often designed to be kind of very robust, often with very proven rigid APIs designed to do one specific task, like a weather service is designed, that's the API, that's the spec, it works well, been tested very properly, and that's the scope it does. So it moves and it behaves in a very specific way. And of course that has a lot of benefits, and I'll come back to that later. GenAI, on the other hand, is a much more malleable technology, which could, if it can live up to the promise, could enable software to become a bit more organic in nature. And have the analogy with a knee, where a knee is a bit more flexible than this rather mechanistic way to integrate applications and services, but where you may slightly overstretch your knee, and the way different components work together, you can have this additional malleability built in, where GenAI can help solve and bridge the gap more organically. Probably you still want to have rather purposeful interactions. You don't want the knee suddenly to transform into something completely different. And the analogy I always make, if you have something like a weather service API that is partly driven with GenAI technology, you don't want it to transform into a baking application in most cases. And so there's some limits in terms of the malleability that you want to have if you want to have more GenAI native software systems. Now, as we all know, also GenAI introduces a lot of challenges and complications. One of them being unpredictable responses. So it's not like if you run this function 1,000 times and it's been well tested on a particular input with traditional software, you will get the same response if it's a deterministic application. With GenAI, it's slightly different. Even the same prompt, the same input, or slightly variations, different variations of the input can already produce very different outputs. Also, kind of migrating from, let's say, one version of a particular system to another version. This was actually from a website that I saw 2 years ago. Where they were actually arguing with traditional APIs, if you go from spec A to spec B, it's obvious, or quite obvious and easy to kind of adapt all the other components to be compatible with the new version. With LLMs, it's not that trivial. And they were claiming at that time that you need to kind of have fixed LLMs underneath to try and keep your application more predictable. But I would argue that this is kind of a misleading approach because, as we all know, slightly different inputs can result in very different responses. And so if you want to build software systems that have some LLMs or GenAI or agentic capabilities inside them, we need to wait to design our systems to be tolerant against the fact that even at runtime, the responses may behave quite differently and not always be as predictable. One additional kind of thing is that as you go from version A to version B, the same with LLMs, if you change the LLM underneath your agent or underneath your GenAI asset, it's unclear what that change will entail. Here, often you can very precisely say, look, I'm going to change that parameter, or I'm going to make that will change, and kind of a very surgical precision mechanism. If you change the LLM underneath your agent or your asset, in some parts it may have come better and operate better, but in others it may not have been. And so you have this issue that you need to have a system that is resilient to these underlying changes. And so it's a bit, the analogy I always make is if there's a new team member joining your team, the dynamics of the team will change. We know that you cannot expect from that team member to behave like the previous team member. We always have to change and adapt towards, okay, how to interact with this new capability. So imagine a future GenAI-native system that is full of agents. The moment you have to change the LLM, and these days it happens every 6 months to a year, there's better versions, your system may change, the behavior may change, and not in a traditional predictable way that you can easily fix by just making a small change. And so that also requires a different way to how to build software systems that can be robust and more tolerant against that. Another issue with GenAI is what some people have dubbed jagged intelligence. And jagged intelligence is the fact that on some benchmarks, it actually is achieving superhuman or PhD level, as they claim, performance. And actually, they're eating benchmarks for breakfast. Whenever new benchmarks comes out within the next few months, they're basically roughly solved by new versions of LLMs. On the other hand, and I've seen this, this problem, it's quite popular, it can stumble over very basic problems. And so if you want to build reliable software systems that have GenAI components in them, how to tolerate with that, how to deal with the fact that even on simple problems, it can slip up on some occasions. And there's many other challenges with respect to privacy, trust, and security that I will not discuss further in this talk, but that are still very important. As we all know, GenAI is very malleable to prompt injection attacks and others. So if you build a software system to deal with that, there's all kinds of issues you need to take into account as well. Now, our position is if we want to have future software systems that also have GenAI capabilities in them. So On the one hand, if you look at the traditional system, you could say that's a form of pure exploitation. So it's built for a purpose, a specific purpose. And so all the tools and capabilities are focused to improve reliability, the operational excellence, and ensure that it works as supposed to be. In the AI engineering community, there's this push towards let's identify everything, let's just throw agents at the problem and they will solve everything, they will run the workflows and things like that, which I would claim is more like a pure exploration mechanism. It's like putting humans at the task for every single task, every single time. Our position is that to build an effective future system that has GenAI capabilities in them, you probably need something like in between. So where you want, for most cases, you want the reliability and operational excellence, but a bit like the knee, you also want a bit the creativity and perhaps the evolvability of a system, not being rigid, but the capability to evolve beyond its original specs. And finding the right balance will be the key here. Just to make it a little bit more concrete, and in the paper there's more examples. I try to find, okay, what's the most basic problem where it could make sense, and where I can explain some of these principles. But it actually applies to the entire stack for building a software system. So if you look at the smallest problem, it could be like a parsing function, where if you would try to implement that with traditional mechanisms, often you would use some kind of regular expression on some heuristics, where you also make a priori assumptions on the types of inputs you'll be able to process. You make assumptions like, okay, it comes in this structure, often structured or semi-structured, it has some properties, and then you build your regex and things like that, and it will work flawlessly, very efficiently for those types of inputs. At the other extreme case, you could say, no, we just feed it into an LLM, and the advantage of an LLM is no matter which format it has, whether it's structured, unstructured, whether it has another modality, an image, or even an audio fragment, these days you can just feed it to the LLM, and if you ask, okay, I want to extract this type of information, it will do a pretty good job. It may not be as reliable, it will consume much more resources to be able to do that, but it's much more flexible. In terms of being able to handle a wider range of inputs. But so, GenAI-native, what does it mean? So what we think is that in the end, GenAI-native should be building in tolerance. If you have this cognitive capabilities, this GenAI component in them, to be more tolerant against the fact that it is not always as reliable as a traditional function. But on the other hand, you want to still have kind of the system overall striving for excellence, operational excellence. You don't want to have the agent in the loop all the time if it's not needed. Now, to make it a bit clear why and how this may be different from traditional ways, if you look at a traditional function, and on the y-axis you could see it's kind of a density distribution of how you want your output to be. If you design it, typically a traditional function is designed kind of with a pass-fail, where you want the output, given a particular input range of inputs, a perfect answer, and you want the system, the algorithm, to be also quite certain about that output, and so that then other components can rely on that and compute based on that. A GenAI component is inherently different. It's not like, okay, pass-fail, it's not always this perfect, but it's more like a distribution, a density that is somewhere blurred, and depending on the types of inputs, you will get, on average, a better score, but not always a perfect score. And the component will also not always be perfectly certain about that answer. And so the argument is that rather than going for this pass-fail, to have something like, okay, let's redefine the passing rate and look for something, okay, is it sufficiently useful? So if you think of a function like summarizing a piece of text, it's often hard to uniquely define what a perfect summary of a piece of text would be, and can be also very personal depending on who's asking that. And so rather than going for perfect and certain, the other alternative for such components is to build systems that can tolerate also different levels of perfection in terms of quality and of certainty with respect to the response. Think of an image classifier that needs to detect pedestrians. Rather than striving to always get it 100% correct, let's build a system that can also tolerate inherently the fact that it may not be certain and always be perfect answer, and build resilience around that to compensate for the fact that it's not always a perfect answer. Now, in cases you do trigger a GenAI component or asset, and it produces some output, ideally you have a system that, for example, can self-assess okay, it's actually subpar, it's below the sufficiency threshold, and then can make corrections. I mean, it's something we do all the time. If you want to make, for example, slides, you start with one version, you kind of iterate over that, you say, oh, this is not good, and you try to fix it. You can ask for feedback to others to try to further improve it, to get to somewhere, and then at longer term, you could even say, look, I will train myself in becoming better, more proficient. And so by changing the LM underneath, or by changing the asset whatsoever. Of course, this takes time. And so that's also something. GenAI has an inherent overhead, not just the processing, but all the resilience and efficiency that you would need to compensate will add some overhead. And so that was something to take into account. I think a month or so ago, I saw on a newsletter from Simon Willison that a similar argument where they say, okay, if you think about it, software engineering, but like unlike traditional engineering approaches, in some sense had, for many use cases, the luxury of deterministic expectations. This input in, and we've tested it, we will get this output out, and can even prove it, and things like that. With GenAI, this goes out of the window to some extent. And there's a lot of effort to try to minimize that as much as possible, but in the end, it still remains more like a probabilistic capability and function. And so we should treat it as such as well when building such a system. Now, in the paper, we argue, okay, about, okay, what would be good design principles and patterns, and I'll discuss some of that in the next slide. But I also want to make some analogies with previous technological transformations. One being IP networking. I mean, this predates even me, but in the past, there used to be circuit switched networks, basically direct connections from A to B, which worked fine at the time until, of course, data became more, and the networking load became more varied, and then they switched to packet switch networks. And to compensate, this actually allowed for better network capacity by packetizing data transmission, but caused a lot of issues. Issues because, okay, packets could be lost, could be arrive out of order and things like that. And so additional resilience mechanisms were built around that and on top of that to compensate for that, either in the layer itself, but also layers on top of that. Think of HTTP adaptive streaming as a way to tolerate, to be resilient in the fact that the network bandwidth or latency may not always be the ones that you want. And for many applications, that is good enough. For some applications, and in Nokia, we actually sell virtual network slices for applications that really require a particular latency or quality of experience, that you can get that. But for many applications, web applications and others, being resilient is good enough, and tolerate the fact that the IP network may not always give you the quality of experience that you may expect. Let's say 10 years ago or something, you saw a similar shift with cloud arriving, where we went from monolithic applications to cloud-native applications. The idea being that we want to be able to have better use of our resources and be able to better tolerate different application loads. For many applications, the solution turned out to be, okay, let's from the ground up redesign how applications should be constructed to compensate for the fact that your system resources underneath may not always be as reliable. And so here we built in capabilities with respect to the communication that is not always reliable. Here we redesigned applications from the ground up to be more resilient against the underlying resources and the runtime not being as reliable. And to tolerate and compensate for that. Think of load balancing, scaling, and things like that. The nice thing about this is that compared to the original monolithic applications, where you often have this active-passive standby in case something would go wrong, these new architectures are inherently more resilient, even to issues that have nothing to do with cloud-native aspects. And so if a node falls down because of a power outage, the elastic scaling and load balancing can automatically switch to others. A downside is that these applications are inherently more complex. Cloud-native applications have more running parts and are more complex inherently. I would argue that if you want to have this resilience layer to also include GenAI components and capabilities, probably you will need to take another step to do that. Now, with respect to the processing, that's the last part. GenAI is a way of cognitive processing. And the best analogy we have is us humans. And I don't want to fall into any anthropomorphic pitfalls, but I think there's a source of inspiration because in some sense, the way we organize ourselves in a company, in an enterprise, in an organization, is also in many cases to deal with the fact that we are inherently also make mistakes every time. And we build in these additional resilience mechanisms like reviews, testing, feedback loops, objectives, goals, and things like that in our organizational structures to compensate for the fact that what we produce on a daily basis is also not always perfect from the first get-go. And so you could say that future software systems could be more like digital or organic enterprises, where there's additional layer and compensation built in, where we not expect from the get-go that the output of one component can just be taken in for granted and be computed further on. But we need to add these additional layers of resilience and mechanisms to be able to tolerate that. And so in the paper, to describe, okay, what does it then mean with respect to design goals and principles? So we centered that around 5 key pillars. Assurance, which is more about security, safety aspects, reliability, operational excellence, self-reliance, having these agents that autonomously can improve stuff and things like that, and as well as evolvability. And then I will not go into this in detail, but in a paper we really focus, okay, what could be good design principles and practices to take that into account. Starting from the existing software design principles and seeing, okay, how we need to adapt and evolve them, but also take into account more from the AI engineering communities, okay, what could be better ways. And then from that on, we also look at design patterns, initial kind of building blocks or blueprints that could be used to build such systems. I don't know, in sake of time, I'll have to... 5 minutes? Yeah. I'll go quickly. So if you have a GenAI-native asset or a GenAI-enhanced asset, if you compare that to a traditional software system, typically you have an input coming request, it does the processing, you get the response, and you're done. Our argument is that if you have a GenAI-native asset, as I said, you need to add some additional capabilities to kind of first internally try to see, okay, is the answer that I'm producing correct enough? Potentially even ask for disambiguation, kind of converse with the component that is triggering you, whether you fully understood the input and the task you're about to do. But then also then if you send in the output either downstream or back to an asset or to a human, not just send the output, but potentially include additional metadata in the response, like your assessment score, or additional redundancy mechanism that then allows the receiving component to make its own assessment, like, is this response that I get, is it sufficiently useful? Is it doing the job that I asked it to do? And if not, have this feedback loop to be able to improve upon it until some point. And so your traditional request-response capability becomes much more complex So that's something, okay, how to build that in. But if you think about it, that's also how we operate on a daily basis with each other. And so that's kind of an analogy that we should take over. Another is with respect to kind of the improving the operational excellence, because in the end, you don't want for all inputs to run them through agents or LLMs, because they're very slow, unreliable, and things like that. You want to have a system where, for the most cases, you can still rely on traditional capabilities. For the cases that you haven't covered with your traditional functions, you want to have kind of more agentic and cognitive capability, but then also have a system that is not static, but that can learn over time to translate kind of things that it does the slow way by hand and to turn them into more traditional logic. And then also redirect from a user experience or user interface, new APIs, things like that, to allow other components or humans to use the fast route. And then, okay, I'll not discuss this in detail, but we thought, okay, how could this look like as an evolution of the as a microservice architecture? And in the paper we called it GenAI-Native cell, where depending on where you come from, if you come from traditional, you start from traditional logic, but you add these additional capabilities and routing capabilities to communicate with the outside world, with other cells, and in a way that ideally most of the time you can still rely on traditional logic, but for the cases that are not covered by the traditional logic, can fall to partial agentic processing. This is the part I said earlier. It's not just request response, but you need to add this additional resilience and communication as well. And it's not a static system, it's a system that can learn to improve itself over time, transform more agentic processing into traditional logic, but also kind of improve the way these cells communicate with each other. So to conclude, in our team, we started looking, okay, what could be architectural blueprints, and okay, how to program such systems, and also, okay, what does it mean, how to improve the reliability from the ground up and robustness. But it's also kind of a call to action for people interested in joining this work to think about, okay, how should future GenAI enhanced systems be built from the ground up and rethink some of these principles. If you want to learn more, I have a poster later today to discuss, and okay, there's also the paper. Thank you.
So in your presentation, you basically saw the AI or the generative AI as a black box, and you argue to build systems around it to solve the problems with reliability and so on. Mm-hmm. So my question rather is like, there's a lot of research in explainable AI.
Yeah.
So how do you think that would fit in this story?
Yeah. Well, it's very interesting because so what I present today is kind of top-down thinking, and that's work that we've done, let's say, last year and beginning of this year. But in the team, we're actually specifically focusing from the ground up, starting from the AI model with whiteboxing techniques to see whether to what extent we can actually do whiteboxing, probe the mind, and use that information to then help steer the programmability and the overall system. And so we're actually tackling the problem from both ends. But looking at it from just the model itself will not be sufficient. Mm-hmm. So you need some leverage and a way to kind of bridge the gap anyhow. Thanks.
Thank you. The topic is actually very interesting. In my team, we have some problem, like say rate limiting, right? You want to rate limit for certain services. You want to know current system CPU memory usage throughput, whether it's good or not. Based on that, you decided whether you accept overload request or not. For that, if you want to use AI, it's kind of risky, right? Because if there are decisions that could be wrong, you actually just reject users' requests with not a good reason. How you prevent that? How you make sure that the solution AI made is robust enough to be used in this kind of context?
Yeah, I think in general it's very application dependent, I guess. It's a problem we have also in our in our routers and future routers, where also, okay, we need to be more and more using AI, not just GenAI, but also AI technology to be able to, rather than using traditional heuristics, to be more effective and efficient. But indeed, in some cases...
It's also more determinative, right? If we use a traditional machine learning classification.
It's yes, and it will work well for the cases that heuristics are, let's say, are working in some sense, but in other cases it may not. And so, in some sense, we're looking at, okay, how a GenAI first or AI first approach could actually, in most cases, could improve the situation. But indeed, you need to then add this additional checks and capabilities to ensure that if it predicts something that is not good, and it could be with simple checks or another system that kind of does an additional kind of sanity check before you make the actual decision. To have this capability in that. So it's a bit related to, if I can quickly go back to this one, to have this additional component in there. Now, this could be an AI component itself, or it could be kind of a simple if then that component.
Right.
So before you send it out, to actually make some quick checks first, sanity checks, things like that.
Right.
And you can either improve in spots, or you could say, no, this one didn't work, I will just fall back to a more traditional capability. So that could also be an option.
Right. And also for the load balancing, you're also trying to use some GenAI in order to improve the load balancing, right? For that, the speed is very important.
Yep.
I agree with you that maybe the traditional LLM model maybe is too slow.
Yeah.
How particularly you solve this problem with caching? With a specific method in order to learn from the past, in order to accelerate?
Yeah, again, this is still kind of paper thinking.
Yeah.
And so we're now starting to kind of try to implement and validate some of that. But indeed, it's this the high-level idea of this programmable router is that ideally it needs to be able to decide, okay, how will I process this? And yeah, if you want the fast path to remain fast, you cannot put a very slow component in front of that.
Yeah,
otherwise you kill your performance.
Right.
And so the idea here was that, imagine you have, I will use a REST service as an analogy here.
Yeah.
Ideally, you could have, if you have for your REST service already a traditional implementation there, you could associate with that a traditional API REST call, and so have a direct route from the route call towards the logic. And so kind of bypassing most of it as a fast path, also in terms of the routing. And only for the cases that are not covered, you can actually kind of gradually go to more slow paths. And so for the load balancing as well, you would ideally you want to have your fast path end to end so that there's no slow component in there. And only for the cases where your heuristics and your things are not working sufficiently enough, you can fall back to the agentic processing.
I see.
On top of that, you could have also something that then observe the behavior and then if it detects kind of inefficient paths, try to see, okay, how to improve the system. And then that's a bit the evolvability aspect, that you could really redefine this on the fly and learn the system to behave more efficiently over time.
Thank you.
Okay.
Thank you.
Thank you.
Sorry for taking.
Any other questions? Let me give some maybe quick questions.
Sure.
So it seems that you are saying that the AI-based system, AI-based software still has a kind of bug, and the bug has to be fixed. But as you presented, in some cases, the user's input might have to be changed. So, for example, if the system suddenly stops answering the question on weather forecast, then the user has to change the way of using the software. So, do you have to? Don't you consider that kind of cases in a process of software development?
Yeah, but I see it more like as a conversation. So I'll not use a human, but imagine another cell, another component that has this capability hidden inside. Ideally, they learn how to be more effective in communicating. And so the analogy with humans would be that if my supervisor would ask me to kind of make a few slides on a particular topic, I may first want to disambiguate to be sure before I do any work, and then I get the results. Now, if the results would be insufficient, over time he can learn, like, I need to add this additional context information so that it gets, I get a better result from the first start. So improving how to communicate with each other. Now, of course, if this cell would suddenly completely change its capabilities and behavior, that's indeed an interesting kind of force field. Okay, what does it mean for the receiving or the communicating components? Do they then have to look out for another component that can kind of solve that problem and then meet their expectations? Or is this kind of like a pushback to make sure that the analogy that the weather service doesn't turn into a dating app kind of capability, and to restrict the evolvability capabilities of the cell itself, so that it, in the end, it still does its core job. It serves its customers, because in the end, you could say it still wants to serve its primary customers, but it can mean that it's evolving to something that also requires changes to the surrounding components, which is also somewhat different from more traditional systems. Okay. And indeed, the interactions there, I think that's still a study on its own, I guess.
Okay. Thank you.
Thanks.
Thank you very much.